All right, here's a short review for homework number 6. We're going to need to calculate the rate constant and the rate law for this one, as well as the orders for each reactant, because we can't figure out the rate law without the orders. And so our orders for this, if I choose trials 1 and 2, I get no change, and here I get a change of 3. And so what happens here? So what is the difference between 580 and 5,220? Let me pull my calculator out here. And so if I take 5220 and I divide that by 580, I get 9. So this goes up by a factor of 9. So the order with respect to the oxygen is second order, because 9 will only equal 3 if it's raised to the second power. So it's second order with respect to O. And how about the hydrogen? So what I have here is a 13.5 is my concentration, and I started off with a 4.5. So let's do, this one's kind of tough. Let's do these guys. And so my concentration change here is a factor of 3. And my concentration change here is a factor of 2. So there's no time when the hydrogen stays constant. So that's kind of a pain in the butt, but that's not that big a deal. So we'll have to do a little factor tree thing. And so what is the difference between this 62,640 and 580? The difference there is 108. 108. Okay. Well, how much is this going to change? The oxygen, we already know, is going to change it by a certain amount. And since the O2 is controlled by a second order, that means it's going to change it by a factor of 4. So if I factor tree this out and I take a 4 away, so 108 divided by 4 gives me 27. So this right here is due to the oxygen. So that means this here, the hydrogen, must be responsible for this 27 value. So I've got 27 and I've got 3. So what number needs to go right there? So what 3, when it's raised to the third power, that's 3 times 3 times 3, and that's going to give us 27. So it must be third order with respect to the H2 and second order with respect to the oxygen. Okay, and so I would plug that into a rate law. I would solve for K is equal to rate divided by H cubed and O2 squared. So we can use 580 divided by 4.5 cubed and 2 squared and get some number here. Let's see what that number is. So 580 divided by 4.5 cubed divided by 2, I'll just say divided by 4. All right, and so my rate constant is 1.5. It's going to be 1.6. So then my rate law is rate is equal to 1.6 H concentration cubed and O2 concentration squared. Okay, so that's number 1. And number 2, if I add calcium metal, Ca solid, to a solution that contains iron ions, will a reaction occur? The answer is yes, because iron is higher on the calcium is higher on the list. So calcium would want to give electrons to iron if it could. So can it? And yes, calcium has its electrons and iron is missing electrons, so calcium could give electrons to iron, and it would. There would definitely be a transfer of electrons from the calcium atom to the iron ion, and you would end up with calcium ions and iron metal. If I add magnesium metal, Mg solid, to a solution that contains sodium ions, will a reaction occur? And the answer is no, because sodium is higher on the list. So that means magnesium will not give any electrons to anything higher on the list. And since sodium needs the electrons, it doesn't even have any electrons to give. So it cannot. So this next one here about drawing a cell. So I've got And then nickel, magnesium, doesn't really matter. I'll put magnesium over here, and I'll put nickel over here, and I'll draw voltage and voltage. The electrons are going to be transferring this way because magnesium is higher on the list. In the solution, I probably got nickel ions in some form, maybe nitrate. That's fine. Negative and a positive, 2. And then magnesium, we'll just pick something easy and say that it was magnesium chloride salts. And aqueous. And then I have a salt bridge, and in that salt bridge I'll put, I don't know, potassium chloride. And that's it. The half reactions for this are going to be magnesium solid turns into magnesium ion plus 2 electrons. And then we've got nickel aqueous plus 2 electrons equals nickel solid. And so since it's 2 electrons on the right side and 2 electrons on the left side, those guys are going to cancel out with each other. So we'll go ahead and get rid of those, and then we'll just add this up. I've got nickel aqueous plus magnesium solid, and on the other side of the arrow, I'll clean that up a little bit. Magnesium solid. On the other side of the arrow, I got nickel solid, and I've got magnesium. Ugh. Oh goodness. I've got magnesium aqueous. So I know off the top of my head, actually let's just go ahead and go over to the notes. So the notes, where are they? No. Notes, 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 notes. Notes. So let's go ahead and go down here. And our voltages that we're looking for are the magnesium voltage, which is right here. Oops. Let's undo that. Oh goodness, really? The magnesium voltage that we're looking for is right here, but it's written backwards, and that's okay. And the nickel voltage we're looking right here is written correctly. So I've got this number and that number, and so I'm going to have to flop the signs on that. So I've got 2.38 volts, and what was the other one? 0.23 volts. Negative 0.23 volts. So 2.15 volts is how many volts that this particular cell will generate. That's pretty high voltage. Okay. Is there anything else on this? Oh yeah. Okay, so write the balanced chemical equation of carbon monoxide gas and chlorine gas, and they're going to make phosgen. I'm going to write aqueous, and it's a gas. And that's balanced. That's pretty easy. Pick 2 metals from the activity series, write down the initial conditions for a spontaneous reaction to occur, write 2 more with no reaction to occur. Okay, so I'll pick sodium solid plus magnesium aqueous, and I'm going to end up with sodium ions and magnesium solid. And so that's a spontaneous reaction. And the non-spontaneous reaction, I can have, let's say silver, solid, and iron, ion. And that's going to be a no reaction because the silver is lower on the list, so it definitely won't give its electrons to the iron. Okay, so equilibrium expression for this reaction. So I've got K is equal to CO2 squared CO squared O2. Calculate the equilibrium constant for those reactions. So 2.5 times 10 to the negative third squared times 1.6 times 10 to the negative third. And then over the top I've got 3.2 times 10 to the negative 2 squared. Alright, so that's going to take me a little bit to punch that into the calculator. But I got 3.2 E 3.2 E negative 2 raised to the second power. And I'm going to divide that by 2.5 E negative 3 close parentheses raised to the second power times 1.6 E negative 3 close parentheses, and I get 102,400. That's a big equilibrium constant, but that's what it pops out as. With 2 sig figs just end up being 100,000. All right, so let's look at this. I've got, you add hydrogen, how does this equilibrium shift? If I add H, then it's going to shift in this direction. If you remove acetic acid from the equation, okay, so if I remove acetic acid from the equation, we'll do red for the second one. That goes away, and so the reaction is also going to shift to the left to replace the acetic acid that was changed, or was removed. All right, that's it.